So I'm really happy to be here and to discuss with you a number of issues related to the future of farming. So providing food security for the world's growing population is one of society's grand challenges. And population modelers are estimating that by 2050, so a little bit less than 30 years, we'll be approaching 10 billion people. So population growth is expected to severely challenge our food production system. The United Nations estimates that if we fail to act, that there could be food shortages by up to 70% on a worldwide basis in 2050. This is the World Hunger Map, and obviously it's not equally distributed. The majority of the crisis, of course, is in Africa and parts of Asia. But the issue of food insecurity is also a local one. When I started talking about the future of farming and SmartFarm concepts about 5 years ago, it was lower. Currently, shocking, 1 in 5 people in California, so about 8 million people, do not have enough food each and every day to lead a healthy and active life. So this would be as if Marita stood up and Beth stood up and someone in the first row. That would be, 1 in 5 individuals, right, in California. So even though we produce the vast majority of fruits and vegetables, we have this crisis. And it's not equally distributed amongst age groups. The food, I don't actually have the current number for today, but a few years ago it was 25% in children. And if we look at low-income students in the summer, when the school lunch program is not available, it's a shocking 85%. So no family should have to choose between paying rent or buying food. They shouldn't have to choose between homelessness and hunger. No senior should have to choose between buying medicine and buying food. No parent should have to skip a meal to feed a child. So in order to prepare for the future, we have a number of challenges. So hunger is a very complex issue with lots of factors: distribution, socioeconomics. But on our side, we need to be prepared to be able to produce this healthy and nutritious food. And there are a number of challenges facing agriculture to be able to do that. And so I'm grateful to Erwin for putting this workshop together so we can talk about a lot of these technologies. So it is a very shocking and challenging environment, but I'm very optimistic that we have the opportunity between all of the resources that we have. So speaking of resources, we must find new and more efficient ways to produce food while minimizing and very wisely using our resources. And in the West, I'm sure you're aware, many of our areas in the West are in extreme drought. So water is a critical resource that we need to be managing. We are currently in the so-called era of farm labor scarcity, right? So this is another challenge to agricultural production, and particularly in produce, right? So if we're talking about grain crops, there's a lot of automation available if you're talking about wheat or corn. But when we talk about produce and their fragility, both in terms of mechanical fragility and perishability, we really have to address this. Climate change is another of the grand challenges. The modeling in California looking at 15% reduction in productivity if we fail to act. And we're very broadly, so I'm an engineer, Erwin's emphasizing engineering, but we really at UC Davis are looking very broadly at technology. So biotechnology and the breeding center are going to play a real critical role in this. We need to be able to develop new breeds of both plants and animals for food production that won't just survive in the climate of the future, but can actually thrive. And so we very broadly think about technology and emerging technology in that way. The pandemic, so this is a shocking scene that, 3 years ago, most Americans would have not thought that this was America, right? And so the fragility of our food supply system, the distribution system, the ability to change, when we stopped going to restaurants and started buying things all in the grocery store, our inability to be easily adaptable. And this is just another shocking piece of information. Erwin, I know, talks about this quite a bit. 1.3 billion tons of wasted food. So when we have a quarter of the world's population being hungry, this is where technologies of minimizing waste, particularly in produce, could be extremely beneficial. So SmartFarm is a shared vision that was first articulated to address this about the time of the birth of the personal computer. You would have imagined then that each one of us would hold in our pocket, a computer that's 1,000,000 times more powerful than the computer used to put a person on the moon, right? So SmartFarm is this idea that technology can be involved in a grand trade, a trade of knowledge for effort, right? It's this vision that the intimate knowledge of each individual, of the needs of each individual plant or each individual animal, can be used to farm or ranch at a commercial scale with the same intimate knowledge you would have in a backyard garden. So if this was your backyard garden, we've got a few lettuce plants and so forth, you know how each one is doing, you're caring for them in a very personal way. And technology is going to be one of the keys that's going to allow us to do that in the future. So these are traditional precision ag maps. So each of these circles represents an important element in the production of food. So that might be soil texture, it could be calcium level, fertility, a variety of things. The one on the right side, each of those individual cells is about the size of a football field, right? So these are things that were fairly coarse resolution. So, in the previous century, this was cutting edge technology to be able to make these maps and to try to understand the concept of heterogeneity and variability. Some of these are updated once a decade, some of them at most once a year, right? So this was a fairly coarse, both temporal and spatial resolution. And the technologies that are going to be discussed in this workshop are really going to be game changers, right, in terms of time and spatial resolution. So Christian Nansen, the professor here on campus in entomology, is doing some really interesting, innovative things of looking at pest control on a very high resolution, high temporal resolution basis. And these kinds of technologies are really going to be important. Unlike most industrial automation targets, agriculture is an uncontrolled, very rugged environment. So the topography, the climate, all of these things are very challenging. We're going to see some discussion about ergonomics and the human side. We have to take a very holistic approach to solving this. This is on the lower right, an individual doing weed control on the California coast for invasive species. Obviously, this is a very rugged and hazardous environment, both from dust and presence of plant care materials. And then this is a tragedy of a rollover incident. So technology is going to have a lot of approaches and opportunities to make an improvement in agriculture, both from food security standpoint, but also from enriching the environment for the workers. This is an example of a project. It was a collaborative project between Professor Ken Giles in Bio and Ag Engineering here at Davis and Yamaha. This is not your small tabletop type drone UAV. This is about the size of a motorcycle. And it actually has the payload capacity to carry plant care materials. So this can apply on a spot by spot basis. Christian Nansen's UAV was trying to distribute beneficial insects on a plant-by-plant basis. So these technologies are really eye-opening opportunities to be thinking about how we can solve a lot of these challenges. So again, it needs to be a holistic approach. There's going to be, vertical farming, big data, robotics, breeding is a key element here, but also workforce transformation and nutrition. So we have a broad range of things that we need to be thinking about. It's going to be conducted, so the idea of smart, right? The knowledge piece of this trade, of a grand trade, of if you know more about the needs and the situation, you can address that. So sensing technology, whether it be permanent sensors in an orchard or whether it be sensors on drones or ground-based vehicles is going to be a key, and then the infrastructure to be able to react to that. Obviously, agricultural systems are complex, right? There's a lot of interactions between a lot of factors, environment and plant variety and pest populations. So SmartFarm is going to have to rely on machine learning. A lot of these big data approaches are going to be some great opportunities for that coming forward. So this cow is wearing a smart collar, so you can kind of think of this as the Fitbit for a cow. And some really exciting technologies are coming in the animal agriculture. So I know this is a produce focus, but agriculture is going to have to address this both on the plant and animal side. So there's a lot of work going on, cutting edge technology, emerging technology, face recognition for cows. This is measuring body temperature and pulse rate. There's a lot of work looking at posture. So again, how do you ranch at a commercial scale and understand the needs of each individual? And so this kind of technology is being developed. We're really excited about this new dietary intake monitoring system. So Helene Dillard seed funded this. So it's just over near the campus airport. And this is the work of Professor Cassandra Tucker. And we all know that one of the first things that occurs when you start to feel ill and poor is that your appetite can decline, right? So you have maybe body posture, and so some of the posture physical pieces of the smart collar, but the dietary intake will change. And so these are intake monitoring systems. So the cow is wearing some kind of an RFID tag. It comes up to eat, and then this is recording exactly the intake of each and every animal every time they come to feed. And so it's really an exciting opportunity to be looking at smart animal ag technologies that she's doing. And so I think that hopefully now that we're going to do more in-person things, there'll be opportunities to tour this facility in person. This colorful map is the work of Professor Patrick Brown at UC Davis. And so each of the colors represents the yield of a pistachio tree. So we've got the yield in pounds here. So the trees that are doing really well are performing above average are blue, and the ones that are performing below the average are in red, right? And so we can see the heterogeneity and the fallacy or the problem of traditional agriculture where you would uniformly apply whatever care that you're giving to the trees in a uniform way. We can see that roughly, a quarter of the field is red, and you think about a quarter of the world's population being hungry, right? So if we could have the ability to understand the needs of these trees that are in red and to apply whatever care they need to bring them up to the average, we could make great inroads in our ability to produce more food. This was a joint project between Bruce Lampinen in plant science and Srini Upadhyaya in my department to develop a smart sensing machine. So it had a lot of sensors here. PAR is the photosynthetically active radiation level that the plants use to convert sunlight into carbohydrate, GPS for knowing where it is, LiDAR is a three-dimensional architecture sensor, and has a lot of various sensors on here. This is a picture of it in a walnut orchard, and what it's doing here, it has a boom, and every foot it has one of these sunlight sensors pointing up, and it's designed to measure whole tree transmission. So you have the sun above, and if the tree is healthy and large, it captures all the sun and converts that into walnuts. But if a tree is doing poorly, a lot of that sun gets through the tree and would strike the ground. So the sensor, there's a bunch of sensors along that boom across the front, and as it drives along, they can capture this. So you have sunlight interception, and you have the nut yield. So this has a number of really interesting opportunities for smart agriculture. First of all, if a tree is only capturing 25% of the sunlight, then it's only going to, so the black line that he's drawn across here diagonally is essentially the performance or the production of the best orchards that he has observed. So if you're at that black line, you're doing really well, right? And so you can see that if you're at 20%, then you're at about 1,000 nuts per acre for that particular tree. So each of these circles is an individual tree, and you wouldn't need then to put the resources into that tree that would allow you to produce, say, 5,000 pounds per acre, right? So you have the ability to, on a resource side, manage and map the resources to the ability of the tree to use them. But you also, from a management standpoint, have the ability to think about what is going on with this orchard. So these blue circles were for a particular orchard that he observed, and you can see they're consistently below the average, right? And so if this is your farm, what is it about your farm that's not allowing this orchard to produce at the level where the well-managed orchards are? And you can look at this from a big data opportunity. So it's this irrigation, pruning, nutrition, a variety of possible implications of how you could rectify that. This is some work that I did with some professors in the College of Biological Science here on campus, is looking at a breeding program for drought. And so this was a relative of the tomato that was drought tolerant, and it was in a controlled environment and being observed by a thermal camera. Okay, and so at the very beginning, all the plants received the same amount of water, and then the water was turned off on half of them. So I've got a green box and a red box. And so the red box will be the ones that get no water, and the green box will be the plants that get continue to get water. And the temperatures are shown here. So we've got the air temperature is around in the bottom corner here, 30 degrees, and the plants are a little bit below. So as the plants transpire, right, they have evaporative cooling, right? So the stoma open, you get evaporative cooling, and the leaf temperature tends to be a little below the ambient temperature. On the next day, then now some of the half of the plants have had no water for a day. And then on the fourth day, you can start to see the color differences here. And so we've got the 36 degrees ambient temperature, but the well-watered ones are a few degrees below, and the ones that are closing their stoma and are not transpiring, then their temperatures are going to be at ambient temperature or above, right? And so here we have wilted plants on the sixth day of no water. You can see a dramatic difference between these two. All right, so sensing technology, this is just one example, is going to allow us to look on a plant-by-plant basis, in some cases on a leaf-by-leaf basis, and understand a particular need. We were one of the first in the country to develop self-organizing networks. So, so now we all go around with our phones and connect all the time. It seems very routine, but this was some of the technology that was developed at UC Davis. It was later on a technology transfer project. So this is a little node, and you could put it, it's battery powered. and it has solar, so it's a rechargeable battery with a solar panel, but it has the ability to communicate with the cloud, so it can send information out and it can receive information, and it has the ability to turn things on and off, so it can open a valve, it can close a valve. All right, coupled with this then was the sensor side. And so related to what I showed you with the thermal sensing, this is an almond tree on the left, and this sensor is mounted in the tree, stays there all the time, and it has a series of sensors. So it has, the primary one is in the middle, the infrared thermometer looking at the leaf. And if the tree goes under water stress, then what do we expect? So the stoma will close, and the stoma closed, transpiration shuts down, and the leaf temperature goes up. So by monitoring that, and if Ken Shackle was here, well, wait a minute, you have to also know temperature of the air. You also have to know relative humidity, right? And you also have to know how sunny it is, right? So yes, all of those sensors are in here. So it's gathering all this information, and it can then see how the tree is responding to the environment. It's connected to the node we saw in the previous slide. So it can talk to the weather app, and it can say, okay, what's the weather going to be? It also has the soil map, so it knows whether it's on sandy soil or what kind of soil. And so you can then project what the irrigation needs are on this situation. And they've been able to save about 20% of the water compared to a just a homogeneous irrigation system and not reduce yields. Obviously, we'd like to save 80% of the water, but these are emerging technologies, and there are a lot of startups that are working on irrigation controls. It's considered one of the lower hanging fruit in terms of automation, so I think you're going to start to see that. This is not a UC Davis project, but it's a really interesting project. It's a Canadian startup, Temios, and this is Internet of Things. So again, it's an internet connected device like the previous slide. It's got insect traps for coddling moth, and it has camera technology, and they're looking at the traps, and as the insects get stuck on the traps, they figure out what kind they are and their population densities. And then, like the other one, it has the ability to do things, and it can just, the pheromone, the mating disruption compound, it could release that. So then this can be networked across the valley. You could potentially look at infestations of insects as they go across the valley, and has the ability to respond. It's also really interesting from a security standpoint because it's on the network, right? And so when we teach our students, right, hacking, we're all kind of constantly aware of having to update our phone. This is another system that would be on the network. And so with the technology comes also some challenges from a security standpoint. When we talk about breeding, a phenotype is an observable characteristic of an individual, and it's an important feedback mechanism that breeders use. So when they map the genome and they know a lot about the biotechnology, and they adapt a new crop, per se, they would have to then test it in the local environment. So these are two students, UC Davis alum now. They were in the wildlife and fisheries biology major, and they were involved with a research project on the western bluebird. And so here they were in the large zoomed-in picture, measuring the size of the skull of the bluebird. All right, so so when we look at the breeding needs and the feedback, we have the genetic information. So a lot of the advances in GWAS, the genome-wide association studies. There's a lot of advances in the biotech, but they also need to know about the local environment, and they need to know about management practices. All of these come together to produce the phenotype, which would be tons per acre or so forth. So UC Davis is very active in this biotechnology area, mapped the genome for coffee, for example, one of Erwin's favorite topics here. Got my finger going here. But the phenotypes are still measured by hand. So as the student was doing with the hand caliper. So we had a project with Dina St. Clair. The students would go into the tomato field, and all the measurements were done by hand. And so this is a definitely a bottleneck. So in order to advance breeding times, bring out new cultivars more quickly, we need to scan to do this all at commercial scale. So this is obviously not an agricultural picture. Here we've got a football stadium, and in this stadium they have 36 of these high definition cameras around this. And this is a little clip from Super Bowl a few years ago. But the point is that with all these cameras, you can zoom in and you can stop, freeze frame, and you can see where exactly the football crossed the line, right? So you can zoom in and see very intimately in high resolution detail information about each player, where their body parts are. So on an agricultural basis, we really want to be able to do this for plant breeding in particular. Okay, so this is a device that we developed at UC Davis, like the football stadium with all the cameras around. It has pairs of cameras, 32 of them, looking at one plant. So all these cameras, so to talk about all these things looking at, that's how it would feel if you were on the ground looking up. All these cameras would be looking at you. And because they're in pairs, they can do 3D stereo. And so you can actually get three-dimensional pictures. So there's a little video clip showing that it can move to find the best view. Hear the clicking, taking all these pictures. Again, these are emerging technology, so a university prototype. This is not an agricultural plant. It was a horticultural plant from the garden center, but you can see how the robot can go. You get all these pictures, and then with a big data approach in the computer, you can make these models. So you can actually zoom in, you can pretend you're a bumblebee, fly in there, look at each leaf. And so the emerging technology here is just really super exciting. I think we have a agricultural plant coming. Yeah, so this is a sunflower. Again, taken in the field now. This is actually on campus. And again, you can see the intimate detail of being able to look at each leaf, look at how the leaves change, insect damage, a whole variety of things. So this is an in-field high throughput phenotyping system. Again, it's taking these 32 images. This is the most recent version that we developed with Dina. And this is a pepper plot. And so I'm going to probably mess up the Zoom, sorry. All right, so this is a still picture. This is on campus with a breeding trial. And so you can see the peppers, right? But this is just one picture, right? I've got all the rest of the pictures on my laptop or my iPad. I'm going to pass this around. It's obviously got the accelerometer in here for gaming. And I'm going to have this game, and it's called tip this back and forth. And as you tip it, you can start to see a pepper from this side or that side or the other side. This is all data in the cloud, a terabyte a day. Right? You can come back and look at this data tomorrow, a year from now. If you have a question, a new question comes up, oh, can I look back at this? You have this ability to every pass through the field collecting this. So every week, as the crop progresses, when did the blooms come? What did they look like? You have this historical big data approach, right? I'll pass this around. If you just tip it, you can see the plants from different angles. Right. So there's just really some exciting opportunities here. And again, the breeders are going to play a key piece in this puzzle because of climate change. And while we're passing that around, this is a sorghum example. So obviously sorghum is a really cool energy crop because it can be grown on marginal land. So we're not taking land away from food crops. And the plant scientists can tell you all the really cool things about its photosynthesis. I probably have to stand in front of the camera. And this is a little robot that goes alongside the sorghum field. It's got a boom here. It can rise up and take pictures and collect data from inside where a UAV can't see. And then it goes up, it'll come down, and then it will drive to the next plot. So it goes plot to plot to plot. So this is for breeding, and it's inside the canopy. All right, switching gears a little bit. In 1975, California gained some fame for banning the use of the short-handled tool. And Professor Fatala is going to talk about, back injury and a lot of issues associated with this. And technology is not just going to increase our yields. We're also looking at holistically improving things. So you would think that with this innovation from 1975, we would be in a better shape. So what did we do? Well, we took their short-handled hose away. Did their back angle improve? No, the organic farms are still hand weeding, right? So this is a big issue in organic crops. And so again, smart technology then can help with this. This is a transplanter that we developed here at UC Davis. And so still people putting the plants in it, right? So they have this tomato plants. So there are 6 people sitting here feeding the machine. There are some developments to eliminate the need for people to feed them. But what this machine does is as the wheel goes around and it's holding a plant and it puts it in the ground, it gets the latitude and longitude of that plant. 5,000 of them per acre, right? So the latitude and longitude of each and every plant is then recorded. So we know exactly where they are, and we can then use that then to provide individual care. In this case, it would be weed control. So this is a miniature robot on the left side, and it has little hose, so they're about 2.5 inches wide. There's red triangles, they're sharp in the front, and we're driving towards Irwin here on the right. And so when you're between a tomato plant, there's 2 of them, they're right next to each other, they're killing all the weeds in the path. And as you go to the GPS location of a plant, you say, I know I put a tomato plant in here. You pull them apart, so the red triangles come apart, sparing the tomato plant. And then as you get past it, you come again. So the clicking sound is a high-speed pneumatic cylinder, and the knives, you can't see them because they're obviously in the soil, coming out and going around each plant. Right, so again, the concept of individual care, if you have all this knowledge, sensing data about the crop, you can use that to provide individual care and to automate things to solve some of the labor shortage issues. Irwin talked a little bit about this, essentially the original concept of the systems approach, right? So this is a picture taken in about 1950 on the Davis campus, and this is Jack Hanna, who had the vision that for tomatoes that we need to be prepared. So this was the comparison between now and then is just astonishing. This was the Bracero program, which was a guest worker program, was in place, and he had the vision to be prepared for the possibility that this guest worker program would go away. Right, and so what did he do? He developed a tomato that had uniform ripening, so it could be harvested at the same time, and had a thicker outer, what is it? The outer surface of the tomato could handle the mechanical abuse of harvesting. And then in the shade is Kobe Lorenzen. He was the lead engineer on this. And what do? They work together to develop both the tomato and the machine, so they allow you to harvest tomatoes. And it transformed the industry because when the Bracero program went away, luckily these individuals had been working for 20 years getting ready so that within 5 years they could switch the industry from hand harvest over to mechanical harvest. All right, so this is a video showing a robot. It's again emerging technology. It's in a citrus orchard, and it's testing the ability to find and pick the fruit. It's dropping them on the ground, so we'll have to forgive it for that. But you can see the camera technology coming along. Unfortunately, you can't buy robots to pick produce. There's under development, and one of the reasons is that in a traditional spherical or vase-shaped tree, the visibility of the fruit, you can't see all of the fruit from the outside, right? And so these are complex three-dimensional structures of branches and foliage. And then, so you can't see them all to find them, and you can't reach in easily to pick them. So this is some work of Stavros Voudioukos, who's going to be talking a little bit later about digitizing the fruit and trees. So they went in and with modern technology do this. They created a digital orchard, but this is real data. So each of these are real tree branches, and the circles are real fruit. So the idea here again is thinking back to Lorenzen and Jack Hanna, what do we need to do? So if you're at the edge of a citrus tree and you reach in 1 foot, how much of the fruit can you pick? Well, a little over 60%. Right? And if you reach in too free, you can only reach about 80% of the fruit. So in this traditional spherical shaped tree, you run into problems of efficiency because a robot that can only reach in a certain distance or can only see a certain amount of the fruit can't harvest it all. This is an example then of a modern trellised orchard, and you can see some dimensions on the picture on the left. This is actually in Yakima Valley. So this is going to take the cooperation of both the farms and the farmers and the breeding side, as well as the machine learning technology to allow the robot to see and pick all the fruit. The challenge is on the breeding side. This is not as productive of a structure, right? So these orchards don't produce as much fruit. And same thing with heads up broccoli. And then you can also have food safety issues because now the fruit is exposed and bird feces can get on more of the fruit. So it's a complex process and it has not been solved, but there's a lot going on in this area. Co-robotics is this symbiotic relationship between a robot and the biological partner in this case, right? And it's looked at as a kind of stopgap measure that in the next 5 to 10 years, we might be able to have these relationships. This is, I don't know if Stavros will be talking about FrailBot, but this is FrailBot on the right, and it is a transport robot. So finding the fruit and picking them, and strawberry, they're so delicate, not damaging them is very challenging. Right? There are startups not commercially available. So what they did in this project was, okay, what can we do right now? And what we can do right now is we can have little robots that can go up and down the rows and they can transport the fruit. So this was a project the students and Stavros were working on. This is the little picture on the robot going up and down the rows, and it can then, the workers are wearing wristbands, and so we know where the workers are, and we have a fleet of these, and these robots can go around finding the workers and transporting the fruit. This is an article out of the New York Times. This is Nissa Scott. She worked at an Amazon warehouse. And she, when you placed your order at Amazon, would walk around the warehouse and get, oh, you want one package of toilet paper, you want various things, and you should put them together in a box and ship them to you, right? And this is an example of the transformation that has to occur because her job has changed dramatically. She no longer physically walks around the Amazon warehouse. There are robots that do that, but she now has to learn how to control all those robots. So this is the interface. So when we look inward at UC Davis, we have to look at this criticism that our existing social structures, especially our educational institutions, are not adequately preparing people for the skills that will be needed in the job market of the future. And so this is the idea that a lot of these mechanical, intense, labor-intense tasks, we need to be thinking about how we can transform agriculture to eliminate them, to make these more rewarding, higher quality jobs. And this is kind of an example. So the tone of the article was somewhat negative, and it was the robots are coming to take your job. But in reality, a lot of those jobs needed to be transformed so that we want jobs that requires to be truly human, right? To be able to think intellectually and to be stimulated by these jobs. And so we need to transform the jobs, and maybe some of these mundane automatable things should be automated. So when we look at this on an agricultural basis, we need to be thinking about how we're going to train the future leaders in the agricultural industry. This picture shows a student in our department. This is up the road a little bit in Yuba City, and we're looking at seedlings that are going to become almond trees. Right now, they are peach trees. And so, of course, almond and peach are closely related. These are nemogard, right? And so on an almond tree, the rootstock of an almond tree has a peach tree root that is nematode resistant, which is what nemogard is. And they plant these by putting peach bits in the ground in the fall. And then they come through the winter. Some of them die. Some of them are eaten by the crows. Every one of these is sold. In fact, I think they've got a 3-year waiting list to get trees because of this transformation of getting away from field crops to permanent crops for a number of reasons. And they go through and they have to count these by hand in order to know how many they have survived and how many trees they can sell that year. And so this was a project the students did to get them out in the field and to bring technology in. So there's a digital camera here. It was taking pictures and it was doing the counting of all of the trees in the field. This is a project that we've done recently in a grad class where the students get hands-on experience with robotics and robotic technology and learning how to, these are autonomous vehicles, not crash into each other and so forth. They're getting experience with developing web interfaces. You can, for $10, get a web server on a chip, right? And so you can have your smartphone talk to this $10 chip, and then you can connect that $10 chip to a lot of things you can turn on and off. Students are getting hands-on experience learning how to pilot drones and do all of the planning and so forth, collect data for that. It's a hybrid program where they get a technology core, but they still need then a background in plant science. Is what Climate Corps called the unicorn. So this is the Aggie unicorn here. We've taken the Mustang and put a horn on them, where they're going to be learning both animal science key information or plant science key information or energy, bioenergy, and then they also are going to be learning a lot of these technology things. All right, we're doing pretty good on time here. I'm going to leave you with a vision of the farm of the future here. So this video clip, so this is obviously a vineyard. In this vineyard, the location of each and every vine has been mapped. It's at a known location. And there would be sensor technology then looking at the care. This is applying a fungicide. Again, another collaborative project between Professor Giles and Yamaha. So Professor Giles built a smart sprayer. Yamaha did the vehicle. So I'm going to let this play here. And when it comes around, I want you to look for the driver. So it automatically turns off the spray. It has the ability to adjust what the compound is and how much of it applies on a vine by vine basis. And obviously it's driverless, right? So in the farm of the future, we expect to be able to have the technology and the knowledge to provide this level of intimate understanding of the needs of each individual and the ability to apply the right response. And with that, I thank you for this opportunity. It's a bit of a teaser because obviously the really cool latest and greatest versions of all this are coming. And so, you'll get to talk to all of the experts coming on what their latest ones. Some of these are a little bit dated, but it should give you an idea of where we're going.
Great, thank you. We do have a little bit of time for questions. I heard that we have some questions online. Beth, you had a question too at the beginning there. If you would like to ask it with the microphone there, and then you can moderate the participants online to ask their questions too, please.
Okay, very good. Well, I'll start with my question, I guess. So I was asking, what is the cost of these technologies and how is it changing? And would you consider most of them cost effective or soon to be cost effective?
So that's a great question, and there's lots of questions in that question. So I'm going to start with the first one, which is cost. And so there was a startup in California. It was called Blue River, and Blue River developed a weeding and thinning machine, primarily thinning machine for lettuce. Right, so lettuce is one of our more labor-intensive crops in terms of weeding and thinning because it's planted by seed. And the innovation, not only in the machine and the technology, which was so good that John Deere bought it, Unfortunately, we're very sad because it's now in cotton and not in specialty crops anymore, but that's a little aside. But the innovation was this. It's kind of like the idea of a co-op, right? So we have Pacific Coast producers, right? And the growers came together to build, in that case, a processing plant where no one grower could afford the cost of the plant, right? So what did Blue River did? They did it on a subscription basis. And they basically said several things. First of all, probably the farmers don't know a lot about machine learning. And they might not know a lot about camera technology. So we're putting, it's like all the Tesla owners, what do you know about what sensors are inside your Tesla and how the algorithm works? So their approach was a subscription basis where it didn't matter how much money you had in terms of capital, you were paying on a per acre basis. So the subscription model is something that we see as very appropriate for a lot of these technologies because you probably actually don't want to buy that machine because the technology is changing so rapidly that by a year or two it might be obsolete, right? And figuring out how to get it tuned and working perfectly. So that's the way that we see a lot of this technology. They made it cost neutral. A lot of times, especially if it's a labor issue, the labor scarcity can be a bottleneck. You can't, in mushrooms, for example, you can't expand mushroom production. And one reason is because of availability of labor. All right, let's see. What are the other pieces?
Well, I was asking about whether the cost was going to change over time. That's a whole different model that you're describing, which makes a lot of sense.
Right. So our weed control machine that we developed with Steve Fenimore was about 50% reduction in labor, and it's not commercial yet. So yes, a lot of these technologies, the tomato harvester, there was an evolution of technologies in the tomato harvester over about a decade. So we didn't start out with color sorters. We didn't start out with dirt sorters. So as time goes on, all the research that goes into this and all the smart people working on these technologies then help to improve them and reliability. So, when Google first came out with some of their, Google Maps and all this, there were bugs in them. And so we hope to see, expect to see them get better. But it might be that, yes, we can't go to full automation or full elimination of some field labor tasks immediately.
So we're going to start off with a question from Maria. Maria, you asked the question. Would you like to unmute yourself and ask the question? All right. I'm going to go ahead and ask your question because I don't see anything happening yet. So she was asking, how much time does it take to implement this kind of new tool or technology, considering the research and prototyping?
Yeah, that's a great question. And, so the robotic harvesting has been worked on for 30 years, right? And we still don't have a commercial version. So it really depends on what we're talking about. We're going to see autonomous vehicles. All the major manufacturers, Honda, Yamaha, all of these manufacturers who have mobile platforms where you have ATVs, they all have autonomous versions of those. They can go into your barn, they can get something, take it to a particular location. So that technology is going to happen much more quickly because the Department of Defense has put in GPS and all of that structure in place. Spray technology is also one that we expect to be adopted pretty quickly because it's much more simple. But picking a strawberry, that's really complicated because obviously it's so delicate and it's hidden, right? And if we have, heads up broccoli, we start where the broccoli head is above the foliage, the yields go down and you have food safety issues. So these can be complicated things that take some time to work out. But, if the choice is I have no workers, or if I take a 20, 30% yield reduction, it still may be economical in that regard. But it's not a uniform answer.
Thank you, David. This is so interesting. You just mentioned the strawberries. I want to go back to the strawberry transport vehicle. As a person who's harvested many ground-related vegetables and strawberries, one of the important things is to be able to stand up, stretch your back. So to me, walking out the harvested container is not a problem. It's a bending over to harvest. So the workers, when that's been employed and tested, what is the reaction of the harvesters to having that robot transport out the boxes of picked strawberries? I'm just wondering, that interaction, the complexity of the interaction between what the human is doing and what the robot can do, does that work?
Right, yeah, so the robot comes up and it's got its tray, empty one, to exchange, right? And it says, oh, no, you can't have this empty tray until you do your calisthenics, right? So I'm joking, but it's really important that we figure that out, because standing up, walking to the edge of the row is healthful, right? And so we have to figure out what are we going to do in that process. And we have this complication of how they get paid, right? So the reaction to them, of course, is mostly driven by a lot of those factors of pay. So in tomato, when we automated, there's an inspection thing, every bottle of ketchup, every can of salsa is inspected by a machine that was developed at UC Davis. And in that process, they had to take an 8-pound container of tomato juice and empty it every minute, right? That was very labor intensive. And so when the machine came in to do that part of it, they were very, very happy. In fact, they hated the idea of it breaking down and having to go back and doing that. So the workers in general, if it is a very labor intensive task that is being automated, and they're working with the technology, so this is a symbiotic relationship, they're very happy about that piece of it. But that doesn't mean that we've solved all the pieces of the puzzle. And so, yes, there has to be some kind of breaks. We want people to take breaks to drink water, and a lot of other safety issues. We need to figure out how to incorporate the pay system so that they're encouraged to straighten up, do whatever is necessary, walk around a little bit for the health side. But the carrying of the fruit doesn't need to be part of that. So currently they're coupled. We need to decouple that. So there has to be some activity that they do to maintain their health. And so when Professor Fadi Fatala comes, he's the ergonomics person. So you can ask again what their ideas about that. But that's a key issue, because we need holistically to raise all boats.
Let's have one more question here. I know we're running a little bit late, but we have some time at the end before lunch, so I could expedite a couple of things that I was going to talk about. So if you have any questions to Professor Slaughter here in the room.
I'm wondering what the population that relies on these jobs to survive, how they feel about the technology replacing that.
Right. So that is a fantastic question. And we actually know a lot about the answer to that, because we did it back in the 1970s when we went to the tomato harvesting. And we didn't necessarily do it well, but hopefully we learned what we need to do. And one of the elements here is, so it happened in rice, and it happened in processing tomato. And so Erwin can post this article. It was a very scientific article from Jim Thompson and forgotten the first name. It was an ag economist and an engineer that looked in a lot of detail about this transition from manual harvest to automated harvest. And one of their conclusions was, so what are the bottlenecks? And if labor is your bottleneck, the industry can't grow. And what they found was that once the transition occurred and the transformation occurred, that both the rice industry and the tomato industry expanded. There was more acreage, and there were more jobs at the end of the transition than there were before. So that automation wasn't a job killer on a long-term basis, but the transition was very hard, right? And so that's why this idea on the educational basis, and when we talk about 4-H and all of these opportunities we have from grade school education all the way through, we need to be looking at how can we provide educational opportunities so that these people can be maintaining the drones. It's like Nissa Scott. She didn't lose her job, but her job transformed into being an operator of robots, right? And so if you have the opportunity then to expand the industry, instead of having, I don't know if you've probably been in the mushroom operations, yes? In between the trays, that's a very difficult working environment, right? But to be able to manage robots that would be harvesting that, right? So the quality of the job, we hope to achieve by technology, better paying jobs that are less arduous, and to be able to figure out how to do the transition better. But we believe that in the end, the jobs will be more plentiful and higher quality. But managing the transition is a challenge, and we didn't do it well in the 1970s. Hopefully, we can learn to do it better.
Thank you for the question. I just have one more question, and it's probably, I would ask you if you could answer it in less than 5 minutes, even though it's going to be tough. But this is the type of question that I get pretty much every day. What I've seen, especially with the development of new technology and everything, is like it opens the avenue to many other companies, like startup companies, to come out. Many are developing software, for example, just software. And a typical question that I get, and you started the talk by mentioning big data, AI, and many companies just throw those words out there. Very, like now we do not need as many sensors as before because I have AI. Now, my question to you would be like, why do you have LiDAR, reflectivity, other wavelengths, and why don't you just rely on just a picture, and then with AI and big data, you can do whatever you want. And that's that. Just to clarify a little bit, why am I making this question? Is we are not having a session specific to AI and big data, but I think that that's something that end users do not understand that well. In other words, is AI that miracle? Is it a miracle? Is it the next thing in big data that's going to solve all our problems, regardless if we have appropriate sensors?
So we're infants in that space, right? We're infants in that space. So Blue River, right, which was this company that is developing a machine for automated weed control and recognizing the difference between the plants and the weeds. And they had a machine, and it was successful in the place they were developing it. And that happened to be Australia. And they brought it over to the United States, and it failed miserably, right? And that's because of this black box approach to AI, right? So AI is incredibly powerful, but it also has risk, and you really need to be an expert in how to mine your data and to use your data and do validation, right? And that's where startups can get into this challenge of running out of money and really needing to put a product on the market. And so we see a lot of products that get rushed. So of not recognizing non-whites, of all of these things are challenges. So we have a lot to learn to try to really utilize the technology. But it has the ability to bring in latent information, hidden information. Anyone who's worked in agriculture knows that these are complex interactions, right? That you just don't apply more nitrogen. You need to know what your calcium level is, right? And calcium then affects the fruit, right? So, Carlos Corsosa's work, and so all of these complex things about that. And if we try to rush the process, and if we take a black box approach, we built a machine for Caltrans. And this machine was essentially holding a paint nozzle over the top of the stripe. So you have your dashed line down the middle of the road, and they have to be painted periodically. And so this machine was positioning the paint nozzle over the top of the old paint. Shouldn't be a problem, right? Except that when you're up in Lake Tahoe, they plow the roads and they scrape the paint off and so forth. And it was an AI approach. And every time we went out, it added neurons to the network, added neurons to the network, added neurons to the network. We got 50,000 neurons, and it wasn't performing any better than what we found is that there was essentially a kernel of information that all of these roads, kind of like Bruce Lampin and all his little dots of every almond and walnut tree, that there was a kernel of information that you could distill this 50,000 neurons down to 7, right? And that if we don't take the time, and this is where the human part comes in, that it took a human to realize that you could distill these 50,000 pieces down into 7 and actually perform much more reliably at recognizing, well, the road slopes this way and the paint wears off the side on this side, and oh, they go around the corner here and they cut the corner. And so all of these various things about how do you recognize worn paint, right? And it could be still down. So we have this challenge of needing lots of information, and we're not as arrogant, hopefully, as some in the automotive industry who have autonomous vehicles and killed a person because a white truck came across and there was a white cloud behind, and they didn't want to have a LiDAR. They wanted just to do it with camera technology. It was, you know, a California car coming off the freeway and unfortunately killed 2 people. So having lots of information and different perspectives can be extremely valuable. And we're probably not knowledgeable enough to answer the question. And we got this question, you know, do you really need 32 cameras, right? You know, can you do it with 18 cameras? Well, we didn't know the answer to that. And hopefully the research can be done very scientifically, lots of validation, and we'll address that. But we're going to see a lot of false or ineffective technology, probably because of the pressure to bring a product to market. And that's one of the transition processes that we have to go through as a society.